Hello everyone, my name is Akash Suryakant Kaude. Today I am here to present my second capstone project, bike sharing demand prediction. It is a supervised machine learning regression problem. Let's start. Problem statement. Currently, rental bikes are introduced in many urban cities for enhancement of mobility comfort. The client is Seoul Bike, which participate in bike share program in Seoul, South Korea. An accurate prediction of bike count is critical to the success of the Seoul Bike share program. It is important to make the rental bike available and accessible to the public at the right time as it lessens the waiting time. Eventually, providing the city with stable supply of rental bikes becomes a major concern. The final aim of this project is the prediction of bike count required at each hour for the stable supply of rental bikes. We have divided our workflow into following steps. The first one is data collection and understanding. The second one is data wrangling and feature engineering. Third one is EDA, that is exploratory data analysis. Fourth one is preparation of data for model building, and fifth one is model selection and evaluation, and sixth one is conclusions. So let's the first one is data collection and understanding. We had a civil bike data for our analysis and model building. The data set contains weather information like temperature, humidity, wind speed, visibility, dew point, solar radiation, rainfall, snowfall, etc., and the number of bikes rented per hour and date information. In this, we had total 8,760 observations and 14 features, including our target variable. Here is the data description of the column. The date is present in the format of year, month and date. Our column is the hour of the day. Temperature is given in the Celsius. Humidity is given into the percentage. Wind speed is given in meter per second, and visibility is given in meter. Dew point temperature is given in the Celsius. Solar radiation is given in megajoule per meter square. Rainfall is given in mm. Snowfall is given in centimeter, and these all are numerical columns. Next is season column, which contains winter, spring, summer and autumn. Holiday is the holiday or no holiday. Functional day indicates whether it's a no functional hours or functional hours. The next one is rented bike count, which is a count of bike rented at each hour. This is our target variable, that is y variable, dependent variable. So this was all about data. So next step is data wrangling and feature engineering. As we know, we had more than 8,000 observation and 14 features. The out of which categorical features are season, holiday and functioning day. The numerical features are date, hour, temperature, humidity, wind speed, visibility, dew point, solar radiation, rainfall, snowfall and rented bike count. So first we rename all the columns because they had units mentioned in the bracket and was difficult to copy the feature name while working. So here you can see we have renamed the columns. So we have removed this units from the brackets and kept simple names. Next, we had zero nulls value in our data set. Here you can see we had zero null values. The zero duplicate entries were found. We checked for the duplicates. Here you can see. We changed the date type of date column from object to date time. This was done for feature engineering. With the help of this, we created new columns, month and day, which were further used for EDA, and later we dropped date column. Here you can see we have changed the data type of the date column, and from that we extracted month and day. So after cleaning data and data wrangling and doing some feature engineering, we started our EDA, that is exploratory data analysis. Here Here we can see the relation of rented bike count with the categorical features like seasons, month, holiday, functioning day, and weekdays. So the first we can see that summer season had the highest bike rent count. Uh, in the summer, highest bike rent count was there. The people are more likely to rented bikes in summer. Bike rentals in winter is very less compared to other seasons, and this is the bike rent count in various months. From March, bike rent count started increased, and it was highest in the June. Here you can see the highest month, June. Next is holiday. High number of bikes were rented on no holidays, which is almost 700 bikes. The next is functioning day. The zero bikes were rented on no functioning day. More than 700 bikes were rented on functioning day. And the next is weekdays or weekend. More than 700 bikes were rented on weekdays. On weekends, almost 650 bikes were rented. Here, this is the bike rent trend according to hour in different scenarios like holiday, functioning day, weekends or weekdays, in different months and different seasons. Here we observed in the first graph. Here we observed that bike rental trend according to hour is almost similar in all scenarios. Here we can see the graph is almost similar in all scenarios. From there is a sudden peak between 6 to 7 a.m. to 10 a.m. Office or college going time could be the reason for this sudden peak on no holidays, but on holiday the case is different. Very less bike rentals happened. Here you can see the green one is the holiday, where less bike rentals happen. In the next on functioning day, there is a same as of no holiday. Only the difference is on no functioning day there was zero bike rentals. Here you can see the green is totally flat. Here the trend is almost similar. We can see on weekdays the bike rentals are higher, and in the sixth month, that is June, we saw earlier the bike rentals are high in the June, and also we saw in the bar chart that summer has the highest bike rentals. But this is the main peak, 6 to 10 am, where bike rentals are high. Next is distribution of our target variable, that is bike rent count. Here we can clearly see that distribution is rightly skewed and some outliers are observed. To normalize the distribution, we applied square root method. After normalization, no outliers were found. Here we can see outliers are not there, and our distribution is normally distributed. After this, next step was preparation of data for model building. With the help of Pearson heat map, we dropped highly correlated variable. As we can see, temperature and dew point temperature are 91% correlated. Here we can see they are 91% correlated. So we drop the dew point temperature because it has very low correlation with our target variable as compared to temperature. Here we can see the rented bike count, and the dew point has 38% correlation, and with the humidity it is 54. So dew point has very less correlation with the target variable, so we dropped it. Later, by using a variation inflation factor, we dropped visibility and humidity features as they had VIF value more than 5. Next, we created dummy variables for season column. Here we can see we created dummy variables for season column, and did mapping with 0 and 1 for holiday and functioning column. Here we can see holiday, for no holiday we mapped with 0, and for holiday we mapped with 1. Similarly, for functioning day, we mapped yes with 1 and no with 0. So thus we prepared our data for model building. So next step is model selection and evaluation. As this is the regression problem, we are trying to predict continuous value. For this, we use following regression models: linear regression, lasso regression, which is a regularized regression. Similarly, ridge regression and elastic net regression, decision tree regression, random forest regression, gradient boosting regression. Before going to the modeling, we'll see the assumption of regression line. There are 4 assumptions. So the first assumption is the relation between the dependent and independent variable should be almost linear. The next second assumption is mean of residual should be 0 or close to 0 as much as possible. Residuals is nothing but the difference between the actual value minus predicted value. So it is done to check whether our line is actually the line of best fit. Third assumption is there should be homoscedasticity or equal variance in regression model. This assumption means that the variance around the regression line is same for all values of the predictor variable x. There should not be multi-collinearity in regression model. Multi-collinearity generally occurs when there are high correlations between 2 or more independent variables. So these were the assumptions of regression line. So before and after applying these models, we checked our regression assumptions by distribution of residuals, scatter plot of actual and predicted values, removing multi-collinearity among independent. So multi-collinear features we have already removed, and this linear relationship we'll check in next slides. And for this second and third assumption, we will check it after applying the models. So here we can see the linear relationship with the target variable with other features. From the above regression plot of all numerical features, we see that columns temperature, wind, visibility, dew point, solar radiation are positively relation to the target variable, which means the rented bike count increases with increase of these features. Here we can see these are positively correlated with the rented bike. All are positive. The next rainfall, snowfall, humidity, these features are negatively related with the target variable, which means the rented bike count decreases when these features increases. Here we can see this line. So this was the relationship, our first assumption. And next is model selection and evaluation. We have evaluated our models based on the MAE mean squared error, root mean squared error, and R2 score. Depending on the R2 score, we are choosing our model. So the first model was linear regression. Here are the scores on trend set and test set. Here we can see R2 score is 0.61 and on trend set, and on test set it is 0.61. It is almost similar. Thus we can say our model performed very well. And these are the graph. This is this residual graph with respect to y predicted is shows the homoscedasticity. So here we can see there is no heteroscedasticity, so this is good. And this is the distribution of the residuals. Mean of residuals should be 0 or close to 0 as much as possible. It is done to check whether our line is actually the line of best fit. Here we can see our mean is almost near to the 0. We have got a nice bell curve shape, and these two graphs are for to check whether how close we are to the predicted values. So this is the linear regression. These plots are similar for all the We have plotted same graphs for all models. These are the scores for lasso. Here we can see R2 score is 0.61, and for train set and for test set it is 0.6172, which is almost similar. And similarly we have got these graphs for ridge. For lasso we have hypertune with the alpha value is equal to 0.01, and for ridge also, here also we got 0.61 R2 score and 0.61.72 on train set and test set respectively. Here also we applied hyperparameter tuning. Alpha is 0.1. This one is elastic net, which is a combination of ridge and lasso. Here we can see, here also we got 0.61 and 0.61 for train set and test set respectively. For hyperparameter tuning we are used alpha is equal to 0.01 and L1 ratio is equal to 0.5. This L1 ratio means taking the ratio both for both models like ridge and lasso, 0.5. The next model was a decision tree with hyperparameter tuning. We took maximum depth is equal to 9. That means we grown our tree up to till 9th node. The maximum feature is auto, which indicates the number of features to be considered when looking for the best split. So that was auto. Here we can see the mean absolute error is 2.88 for train set, and for test set it is 3.39. Similarly for MSE is 18.44, and on train set and on test set it is 24.91, and the finally R2 score is 0.88, and on train set and on test set it is 83. That means our model performed very well. Here we can see we got a very nice bell curve. We have almost residual mean almost near to 0, and here the scatter plot of the predicted and actual value is also good, and here there are no signs of heteroscedasticity. We have not got any funnel type shape here. Next was random forest with hyperparameter tuning. Maximum depth is equal to 9 and n estimator is 100. N estimator means 100 decision trees were created, number of trees. Then here we can see the scores on train set. MA is 2, mean absolute square is 14, RMSE is 3.86, and R2 score is 90 here. And similarly scores on test data, 2.9 is mean absolute error, MSE is 18, RMSE is 4.32, and R2 score is 0.87. Here also we have got a very nice bell curve shape. We are very close to our predicted values. You can see here the scatter plot. Next model is gradient boosting regression with hyperparameter tuning. Learning rate is 0.04. That means learning rate shrinks the contribution of each tree by learning rate. There is a trade-off between learning rate and n estimators. Here n estimator is 150 number of trees, and subsample is 0.9. Choosing subsample less than 0.1 leads to reduction of variance and increase in bias. That's why we chose this subsample parameter for hyperparameter tuning. Here we can see we are very close to the our regression best fit line as compared to other plots. So here we got a good R2 score, that is 0.996, and on train set and on test set it is 0.91, which is a very good score. After these models, the feature importance. Here we can see from all three models, we can say that the temperature over functioning day are the top three important features. Here we can see for decision tree, we for decision tree, for random forest and gradient boosting, temperature over functions are and rainfall are same, giving same feature importances. Here these are the conclusions. As we saw all the R2 scores, uh, as we have calculated ME, MSE, RMSE and R2 score for each model. Based on R2 score, we will decide our model performance. So our assumption is, if the difference of R2 score between the trained data and test data is more than 5%, we will consider it as overfitting. So the first three models were linear, lasso, ridge and elastic net. So models have almost these models almost have similar R2 score, that is 61% on both training and test data. Even after using grid search, we have got similar result as of the base model linear model. And the next one was decision tree regression. On decision tree regressor model, without hyperparameter tuning, we got R2 score as 100 on training data, and on test data it was very less. Thus our model memorized the data, so it was overfitted model. So we tune the parameter, we tune our model, so we got R2 score as 88%. Here we can see for decision tree we got 88% R2 score on training data. On testing it was 83, which is quite good for us. Here we can see on decision tree with grid search we got 83 R2 score. The next model was random forest. On random forest regressor model with hyperparameter tuning, we got R2 score as 98% and on training data, and 90% on test data. Here we can see for random forest we got 98 R2 score, and for test data it is 98. As per our assumption, our model memorized the data, so it was our overfitted model as per our assumption. So we tune our model, we got R2 score as 90% on training data and 87 on test data, which is very good for us. So we have improved our we avoided overfitting here. So next model was gradient boosting regression. On random forest regressor model without hyperparameter tuning, we got R2 score as 86% on training data and 85% on test data. Here we can see on gradient boosting regression without with default parameters we got 86% and on training set and 85% on test set. After hyperparameter tuning, we got R2 score as 96% on training data and 91% on test data. Thus we improved our model performance by hyperparameter tuning. So the final conclusion is that gradient boosting regression and random forest gives good R2 scores, and we can deploy these models. So that's it from my side. Thank you very much.